Okay, and the webinar now is being recorded. So this is a schematics of a common solar standalone system, more concentrating on the wiring and the protection side. And it looks a bit complicated at first, but don't worry, we will break it into smaller sections, which is actually easier to follow and understand. And I will quickly review the big picture here, what you get. So we have different components. The components start from the solar panels. And the solar panels go through an isolator to a fuse or circuit breaker to the charge controller. And then we have our charge controller, which is connected to the battery via a fuse, an isolator switch, and again another fuse, which is dedicated to charge controller. And of course, you might have DC loads in your system. And, this is not depicted in this picture. And because this specific charger doesn't have load terminals on its own. And then we have the inverter, which is also connected to the batteries. It also have isolator and fuses, protector fuses. And then we have our circuit breaker here. Yeah. Okay. Then we have our circuit breaker here. And then we have our AC loads. And then we have sort of monitoring devices that are connected to our equipment and are collecting the data and providing the data for local monitoring or any means of monitoring and control and programming the stuff. And then we have, the batteries, the positive side of the batteries and the negative side of the batteries. And, the busbars that we have here, of course, you are familiar with that. We have the, one or multiple positive busbars or one or multiple negative busbars. Okay, so for those of you who have been present in our last webinar, we have covered the basics of electrical calculations within an off-grid circuit. So the concepts such as, voltage, current, Ohm's law, power, Kirchhoff's circuit laws, and the first and second law has been covered in the past webinar. And phenomena like resistance and voltage drops in inductors and the wires are also covered. And today we'll be using those, terminologies and those concepts to build the wiring section. And wherever is needed, I will just have a very quick review about what we have covered in the past webinars. So we will start with the solar panels. Solar panels are one of the main components of the off-grid system. They come with different technologies, but the working principle is the same. They all absorb the sunlight and generate voltage and current. And a solar panel is normally connected to a specific type of connector, which is called the MC4. Now we are talking about wiring, so we have to talk about connectors. MC4 is connected to the panel, and on the other side of a solar cable could be a wire or another, MC4 connector. But anyhow, you have to get these wires then connected to your charge controller. And the solar charger needs to be placed between the solar panels and the batteries. And the solar charge controller converts the higher solar panel voltage into a voltage that is suitable for the battery and that is suitable for charging. And if the solar panel is connected directly to the battery will get damaged. I know about that. And often we connect the solar panels in series and parallel to increase the voltage and the current of the PV string. And they can, come with different technologies like thin film, or poly or monocrystalline technologies. And when choosing the solar panels, as mentioned before, you have to be careful about the specifications of the solar panel that you choose. One of those specifications is the peak power that you see here. So if, for example, I choose this PV module, with the peak power would be 380 watts, and the open circuit voltage would be 45.5, and the short circuit current would be 10.51. It matters because it will determine the wire size and the charge controller size. So any charge controller that you select must be compatible with the solar array or the solar string that you combine together. The voltage should not exceed the maximum PV input voltage of the charge controller, and the current should not exceed the charging or discharge limit of the charge controller. So let's have a look at an example. In this example, I choose two strings of 4 panels in series, and I select the strings of 4 panels in series, as you can see here. And this means that I'll have 182 volts and something like 21 amps as the input current. And in general, I have 8 solar panels with the power of 380 watts panels. So I'll have a sort of 3,000 watts of PV array. And the nominal array voltage is going to be something like 96 volts here. And having that, I can calculate the current flow in the system by dividing the power to the system voltage. So as I mentioned, the power is 3,000 watts, for example. I can choose 48 volt batteries. So I will have some sort of 63 amps in my system. So this is the power of my solar array. This is the voltage of my system. So I will have in general 63. So this is sort of going to tell me, okay, what size of cable or fuses or isolator or breaker I'm going to use for my system. But this one is a bit, let's say risky, because if for any reason, for example, in changes in the temperature or the charge status, the current exceeds this, then we have a problem. So we normally choose a safety factor of something like 30% for our calculations. And although our current is never going to exceed 63 amps, I'm going to choose 83 as the current rate for my cabling and fusing system, considering only the solar panel part. And if I want to understand what is the voltage, okay, we will have something like 182 volts. So, this will help me to identify actually the requirements for the fuses and the wires. So, about the wiring itself, it's important to use the right cable material and thickness in a system. The more current you have in a system, a thicker cable is required. And the reason for that is that the cable resistance decreases by increasing the diameter of the cable. So you will face less voltage drop in wires. Voltage drop is not desired in off-grid voltage systems because it provides a lot of problems. And voltage drop happens when the current travels through the wires. So if your wire is thin, so it will have higher resistance, and then you will have higher voltage drops in your system, and then the efficiency of your system will be lower, and it will cause other problems such as thermal problems or heating or etc. So to find out the core diameter of a standard core cable, we can look at the cable insulation. Normally there are some writings here. There will be markings on the cable that indicate cable core thickness. And in order to avoid very thick cables, so you might come up with a very thick cable. the first thing you should consider is to increase the system voltage. So, for example, you have a 12-volt system and you calculate your current, and it's a massive amount. But if you choose a 24-volt system for your battery or 48-volt system for your battery, you can still use a thinner cable because you have increased the voltage and the current in your system has come down. And this is the trick, that you can still use thinner cables, which is cost effective also, and still have the same power out of your system. And imagine you increase the DC system voltage. As a result, the DC current will drop and the cables can be thinner. And there is a sort of rule for that. If you're running loads of up to 3 kilovolt amperes in your system, 12 volt will sort of suffice. Now, of course, you can use the 24 volts, batteries for this 3 kilovolt amp system. And then you can use 24, or it's recommended to use 24 for 5K VAs and 48 for the powers higher than 5 kVA. Sometimes there is a technical limitation in increasing the voltage of the system. So, for example, imagine that there is a DC load in the system which works for 12 volts. There is a refrigerator that works for only 12 volts. Then, in this case, you could consider using a DC to DC converter. So it's very important to have a reliable system and invest on a DC to DC converter for that specific load. Otherwise, you will have a lot of losses in your system, and the longevity of the system will be reduced. And if you cannot, on the other hand, if you cannot find thick enough cables in your system, you can use double cables. In some inverters and in some charge controllers, you might face 2 positive terminals and 2 negative terminals for the batteries. The reason for that is that specific unit provides high current, and it's high power unit, and it demands a higher thickness. So the trick here applied is to use 2 terminals as positive and 2 terminals as negative terminals of that inverter charger, for example. And with this trick, you can still use the same thickness, but you are doubling the cables that you are using in the system. And what kind of cable to use in DC solar systems? The material and construction of the cable matters actually. For instance, you must not use cables with coarsened strands or non-flexible cables or AC cables. And the DC cable is entirely different from an AC cable. So you can find online a lot of resources about the differences between the DC cables and the AC cables. The construction is different, the strands are different, and the insulation is different. They are designed for different purposes. So we have to make sure that we are using a DC cable. Sometimes sellers offer a copper clad aluminum wire. So this is aluminum, it's not copper, and which is pretty similar and nice when you look at the cable, but indeed it's not copper. And well, it's aluminum, and aluminum cannot carry the same amount of amps as copper. And so if you use those cables, although you use the right thickness, the current will be limited. And of course, this is not only a problem with using these kind of cables. Over the time, due to the different levels of contraction between the copper and aluminum, because you are going to use lugs here, right? And the lugs are normally copper. And then they will have different contraction levels between each other. And this will, lead to the cable strands cut by time and increase of the resistance and increase of the, temperature in the joints. And this is itself a source of problem, and they might cause fire even in your system. So it's highly recommended that you check you are using a standard copper cable for wiring the system. And for marine or moist situations, you need to use marine cable. I think I have sort of background noise, so I thank you so much for muting the microphone. Okay. Yeah. So another thing to remember is that for marine or moist situations, you need to use marine cables. These are cables with tin-coated copper strands, and if there is any salt or any salty rain or whatever, or the moisture is too high, it's good that you have a sort of tin-coated copper strands, and this kind of cable will stand for longer time in that harsh environment. And another thing to remember is that if the wire is going to be exposed to the UV radiation, then you must use a cable with UV resistance insulation. So the UV component of the solar radiation is known as the main aging accelerator for all of the materials, including the plastic and any sort of insulation. And well, if your cable is not, for example, UV resistant, and you use it on the roof of a van, then by time when this cable is exposed to sunlight, the UV component of the sunlight will sort of destroy the insulation, and then you will lose the insulation of the cable, and it's the source of problem. It might cause, leakage in your system. It might cause short circuit, and even fire in your system. So it's important to check even the insulation of the cable that you are using in your solar system. Well, yeah, but these are also important. Besides cables, we use elements that are important as cables itself. You use, washers and nuts and, all sorts of strings and cable locks and thermal strings and so on. So cable locks are used to connect the cable to a bolt, and it can be a battery bolt or a bolt on a bus bar. We will cover soon what a bus bar is. And the cable lock needs to match the cable thickness. So you cannot use any sort of cable lock with any cable. You have to match them. Even the amount of the insulation that you cut over the cable is important. Then you have to use a special crimping tool to sort of attach the lock to your cable. Sometimes I've seen that people with the unstandard tools like hammer or so, okay, it works at the beginning, but the problem with that kind of pressing is that the amount of the wire that touches the lock is actually lower than the thickness itself. So you have a very high resistance there at your joint, and it will get warm. And yeah, we have seen a lot of failures in the field because of this problem. So the tools that we are using for pressing the lock to the cable and the amount of the insulation and making it water and moisture resistant is also very important. So if you do not cover it by the shrinks, then that will, by time, the cables will corrode, and this corrosion will increase the resistance again, and then it will get hot. So even very small parts of your installation will matter. Again, special care is required when connecting the locks to the mounting surface. This is also important. Sorry. There should not be anything between the lock and the surface. So if you have, for example, a copper bus bar, your lock should just perfectly align to the surface of your copper bus bar. Well, you can put over it, the washers and the spring ring and the nut to tighten it, but there should be nothing between the lock itself and the copper surface. And also, it's important to note that The tightening torque is also important. Sometimes we break a lock or a part of the wire because we apply a very high tightening torque for our equipment and for our locks, and this is also not good. And it's better you use a sort of machine that has a predetermined torque, so that you do not create a resistance variation between your connectors. So if you tighten one too much and the other one a little bit loose, then the area that the locks connect to the bus bar are not the same, and then there is a difference in the resistance level, and this is called the improper balancing of your batteries, for example. So it's better that you apply the same cable length and the same torque and the same sort of connectors, washers, nuts, and springs, and everything should be the same between the batteries, so that all the batteries actually see the same resistance towards the loads, towards the inverter, and the components that resist. So we have covered this in the previous webinar, but I think it's worth mentioning it again here. So we see this a lot in the field, and this is the source of let's say damages to a lot of batteries. What happens here? Why this is wrong? So consider that if you have your loads here, then the resistance that this battery sees between itself and the loads is really too low, because the wire is, the length of the wire is shorter in comparison with the other batteries. So each battery has its own internal resistance as well. So if you compare this with this one, it sees a longer cable distance, and each cable has its own resistance. So this battery sees almost 4 Rs, and this battery sees almost 6 Rs, 3 here and 3 here, 6, and this one is 4 Rs. So this one sees 2 Rs. So what is the effect of that? When the resistance is low, the current will be higher. So the highest current will be for this battery, and then for this battery, then for this battery, and this will have the lowest amount. So this battery will age very soon, because it will deliver a lot of power to the loads in comparison with other batteries, and it will cause a sort of unbalancing in your system, and then it will start to destroy the other batteries as well. And sometimes you will see these batteries are swallowing in the field, and they change their shape because they've been used under a heavy load and under high temperatures. So this will destroy the batteries. So how we can solve this? The correct way of connecting multiple batteries into in parallel is to ensure that the total test of the current in and out of each battery is equal. So here, consider this battery, it sees this length and this length. So this is equal to the length of, between the positive and negative terminals of this battery. So if you draw them separately, you will see that in this system, and this system, and this system, they all see the same path and the same resistance. So this is the correct way of making, paralleling your batteries. And it's also good to mention that the batteries must be balanced prior to the installation. If you buy a battery, if you buy 2 batteries from the factory, they are fully charged, for instance, they will not have the very same voltage. There would be some deviations between those. And, consider that this is, for example, this 13.5 and this is 14.5 in a worst case. And then this will get worse even while you're using the battery, because this will be used more and more and more, and this battery will age soon, and it will destroy the whole, set of series batteries. So it's recommended to charge your battery first and measure the voltages of the batteries on each terminal, and make sure that you start the off-grid system with a source of reliable, balanced battery voltages. And this will prevent the unbalancing problems. Of course, you can use sorts of, let's say, balancing devices in your off-grid system, but Epever does not provide those kind of devices. But you can always easily measure the batteries, even if you want to check your system after 1 year, for example, or 6 months. You can disconnect the batteries when they are fully charged and check if they have the same voltages. If there is a voltage difference higher than, for example, 0.2 or 0.3 volts between them, this is a sort of problem, and you need to think about it and correct the way that they are being charged. Okay, so we talked about the wires and connectors and how to connect the batteries. So let's talk a little bit about the wire size calculation. The correct cable can only be selected once you know the currents in a system. Inverters and charge controllers can experience different levels of current, so you can use different cable thicknesses for each. And you need to look into the product manual first. It normally says what is the cable size or gauge of the cable. So the gauge would be stated on the product manual, which makes our lives easier. We can just easily obey that, and we know that this is this is aligned to the maximum charging and discharging capacity for charge controller, for example, or maximum current that any inverter can draw from the battery. So, but if you do not have access to that, or if you want to make more precise calculation, you always need to find out the maximum current. We did this for the charge controller part, if you remember. We had a current of sort of 83 amps going into the charge controller in and out. And it's calculated by dividing the solar panels watts by the system voltage. So every cable going from PV to charger and charger from the battery must have at least, for example, in this example, sort of 83 amps. In practice, we have chargers with 100 amps capacity, and 83 amps will be safe because with our configuration, the current will never go higher than 83 amps. So you can, after determining this current, you can use the closest wire in terms of thickness that provides this current capacity. And I will let you know soon how to do that. And for the inverter, you might have noticed that inverter have thicker cables. Yeah, there is a specific reason for that. For the inverter, you can choose the maximum surge capacity and divide by the system voltage. So you do not use the continuous power of the inverter. You have to use the surge capacity of the inverter, because there is a reason that this inverter has a surge capacity. It is meant to let specific loads like motors which demand a high inrush current to start in your circuit. So you should account for that amount of current that is demanded by the inverter. Then you take the maximum surge power. For the charge controller, the limit will be the charging and discharging capacity. We talked about it. And for inverter, if you consider that you have 6 kilovolt amperes, then you divide it by your system voltage, which is 48. Then you will have a sort of 125 amps. and then you apply a sort of 20% safety factor. And then you multiply it by 120, you will get some sort of 150 amps. So I repeat it. Take the maximum surge power of your inverter, divide it by the system voltage, you will get a number. Multiply it by 1.2, this is the safety factor, for instance, or 1.3, and then you will get the amperes capacity that you need to provide by the cables. And after you determine this, then, well, you can determine the cable size as well. There are different size calculators or different tables that you can work with to identify the size of your cable. So let's consider that we have an installation of less than 5 meters and I need 150 amps current capacity. Then I'm going to use a cable with the section area of 25 square millimeters. 50 square millimeters. And, well, of course, you can use a pair of 225 cables, but this is what we use. And for example, if for the charge controller, I needed something like 83, so that's going to be 105, the closest standard cable size for that. And then you will need 35 square millimeters for the charge controller. So you can see that the inverter cable is going to be thicker than the charge controller cable. So a question arises here. What if I use a thicker cable for my installation? That's absolutely okay. If we want to make the system, cost efficient and etc. But a thicker cable for the DC cables is always good. So if you have access to a thicker cable, you can apply for that. And for the AC, it's also good, but there is a problem with using a thicker cable with the AC side or AC cables, and that is when you use the parallel inverters. Okay, we do not have, Epever doesn't provide parallel inverters, but in case that you are using other brands inverters, you must be careful that you do not use thicker AC cables for inverters in parallel. There is a specific reason for that, which we are not going to cover that today. So if we want to be quick and short, there is a sort of rule, a thumb rule for that. So it says, if you divide the capacity, the amp capacity, by 3, then you will get a number which is the thickness of the cable in square millimeters. So if I divide 150 by 3, let me see if I can, maybe I can use this. Yeah, if I divide 150 by 3, I will get something like 50. 50. And this is the thickness of the cable in square millimeters. And it's the same. If you divide the amount of the current that you got, for example, for the charge controller, then you will get the same for the cables. So a straightforward and easy thumb rule is to divide the current by 3, and what you get is the cable thickness in square millimeters. Okay, I will change to laser so that we can see my, okay, good. So busbars. One of the other components that we use in an off-grid system is a busbar. So where is busbar? This is called a busbar. This can be a busbar. This can be a busbar. This is the positive busbar. It's also a positive busbar. It's a negative busbar. And this is a fuse that we connect for the batteries. Busbars are like cables, only they are rigid metal bars. So for convenience, some busbars include fuse holders as well. So if you can see, there's a fuse holder, then they have connected some sort of fuses for each component that is going to be connected to the battery. In my case, for simplicity, I have one inverter, and I've used this terminal of the busbar, which also has a fuse to connect the batteries to my inverter. So you can buy a pre-made busbar, or you can create your own. So with a piece of cut and drilled copper or thin copper bar and a few fuse holders, you can create a DC distribution system. Again, for marine applications, you should use a thin copper. And busbars are meant to provide a common positive and common negative terminals between the batteries and inverters and chargers and multiple inverters. And they are also used in smaller systems, especially when there is a lot of DC equipment. So if you have a DC equipment, you can connect it directly to your battery using these terminals of the busbars. If using busbar, its thickness should be calculated as well. It's like a cable and should tolerate the cable capacity that you need in your system. To calculate busbar thickness, simply use recommended cable surface area and apply that to the busbar cross-section area. So you have a width, you have a height, and you have a length, then you can multiply them and you get the area that it has in cubic millimeters. And of course, it's recommended to shield the copper bars. Of course, you can omit the length. So if you get these two here, then you will get the area. So if you multiply the length to the width or width to the height, this dimension I mean here, depending on what you name it, then you will get the area that current can flow to your system, and it's the same as the cable sizing. And of course, it's recommended to shield the copper bars, especially if the busbar is out of, is in an open area, and there is a danger that someone touches it, or I don't know, something falls, and it provides a short circuit between the positive and the negative terminal. So it's always recommended that you cover the busbars, or you put a thermal shrink over the copper so that nothing will touch the copper itself, and there isn't any danger for short circuits. So we will have a short break here. I need to drink some water. And meanwhile, we can check if I'm still audible for you. Then we will start over in a few minutes. So, can you hear me at the moment?
Yes. Yes.
Okay, perfect.
Yes.
Okay. So, I'm good to go. Yes, thank you for the confirmation. Okay. Now the fuses, circuit breakers, and DC isolators. You see now all these sorts of equipment in the market when we are searching for the off-grid products and tools, and it might sound a little bit confusing because there are lots of types of it in the market, and each has its own application. So we will have a sort of brief, short overview of each one. So Fuse or circuit breakers and DC isolators are sort of protected devices, and when there is an overload in the system or a short circuit, fuses save the system from damages. You can now locate the place of these instruments in the wiring diagram. So you see this is a fuse, this is an isolator, this is also a fuse. A fuse is an electrical safety device, as mentioned, and it protects an electrical circuit against high current or high transients. The fuse is placed in the supply cable of an electrical device. And as soon as current flows through the fuse that is higher than its current rating for a certain amount of time, the fuse will blow. Once the fuse has blown, no more current will flow into the circuit, so this is sort of open circuit, and this really protects. So a general rule here is to share. Fuses not only protect the devices and the batteries, but also they protect the wires at first. A device might withstand the high current for a longer time, but cables get heated when there is a high current. And then when they heat it, then they start to, provide fire, and, it's a disaster. So a sort of fuses need to protect the cables. So what I prefer normally in design when it comes to the sizing is that, okay, I might use a cable with higher capacity. As I told you, if I have options for thicker cables, it's always good to use it. But I strictly adjust the fuse current rating a little bit higher, maybe let's say 1.5, maybe times than the maximum current of my system. And I will tell you that there are, time ratings for the fuses as well. So no matter if the cables for a short time are getting 1.5 times the maximum current, but then it will start to blow and trigger, and then, the cables will be safe, of course. So several types of these fuses are available in the market, and they tend to be either confusing. We have ANL, Mega, CNN, and etc. We have the isolators, we have the fuse holders, and we have, let's say, automatic switches or circuit breakers and MCBs and so on. So in general, you have three types of fuses. You have the wire fuse, the thermal fuse, and the magnetic fuse. So traditionally, a fuse contains a wire or a strip of metal that melts as soon as unacceptable current passes through the fuse. And when the wire in the fuse has melted, the electrical circuit has been broken and no more current will flow in the circuit. So once the fuse has blown, it will need to be replaced by a new fuse to make the circuit operational again. This is much cheaper than replacing the charge controller in the system. So it's always good to have fuses in your system. And these fuses are one-time fuses, let's say, and once they have blown, they cannot be reset. You need to replace them. Another type of fuse is automatic fuse, often called the circuit breaker or miniature circuit breaker, or CD or MCB. And these devices interrupt the current flow when high current is detected. So, depending on the type, sometimes they will reconnect after the high current is passed, or they need to be manually reset. And they do not, need to be manually reset. Sometimes they're automatic, they do it themselves, but sometimes you have to do it manual. These do not need to be replaced often. If the case is not really severe, then these are not damaged, and by connecting or reconnecting them, the circuit will be closed again. So there are two ways how these fuses operate, either thermal or magnetic. or a combination of these two. So the thermal circuit breaker contains a bimetal strip that heats up when overcurrent flows, and it bends when heated up, and by doing so it will break the path of the current. The magnetic one contains an electromagnet that is sensitive to larger amounts of the current. When a large current flows the electromagnet, it creates a magnetic force that breaks the path of the current. So we have also ratings for these sorts of fuses, all of them. So we have, let's say, the current rating, the voltage rating, and the speed rating. A fuse needs to match the current rating of the cabling in the circuit. The general rule, as I told, is that you use a current rate which is 1.5 times higher than the maximum current that your circuit is going to experience. We have calculated that for the inverter and charge control. Regarding the voltage, the fuse voltage rating needs to be equal or bigger than the experienced or expected maximum voltage in the DC system or AC system. Yeah, because we have DC types and AC types. And most DC fuses are suitable for 12 volts and 24 volts. But there are also 48 volts, versions, and you can just purchase them. The only thing you need to pay attention is that sometimes you find these kind of circuit breakers specific for a DC or specific for AC application, or sometimes they can serve both AC and DC. It really depends on the ratings of the current and the voltage, both for AC and DC. So if you find a fuse or a circuit breaker, let's say a circuit breaker, that can tolerate the maximum amount of calculated current and in voltage range that you have in your system, then it's the right switch to be applied, regardless if this is AC or DC. So the difference is that you need to check the labeling and the ratings of the fuse to make sure that it's suitable for your specific applications. So, I think, the speed is remaining. So the speed of a fuse is the time it takes for the fuse to open when the fault current occurs. And this is indicated by the fuse material, its mechanism, and the current, and the temperature, and so on. Generally, we have two categories. We have slow blow fuses and fast blow fuses. Slow blow fuses are commonly used in DC applications that can be found in, for example, marine circuits. These circuits contain consumers with a high startup current, like motors or devices, with capacitors like an inverter. And the slow blow fuse will withstand a high short duration initial current, enabling a motor to start, for example, or an inverter to start. So we normally use slow blow fuses for the DC side, and fast blow fuses are used in AC appliances, or even in our setup. AC consumers are often sensitive to changes in flow of electricity, so they need a fuse that can react fast to protect the consumers. So it's good that, for example, consider you are using a laptop in your system. You wouldn't like to have a blow time of 150 milliseconds for a laptop, because that already has damaged your laptop as an AC consumer. So you need a fast blowing system normally here. But it really depends on the type of the loads that you have. Sometimes you have AC consumer that has a high startup current, and this equipment will be something like, electromotors such as refrigerators, air conditioners or so. And in these scenarios, you need to use a slow blowing fuse for your AC part because you have such a load in your system. But in general, to make it simple and easy to understand, we use a slow blowing fuse for DC side and fast blowing fuses or switches or circuit breakers for the AC sides. So let's look at the location of the DC fuses and the circuit breakers and isolators that we have in the system. Each consumer that connects to the battery needs to be fused, and the fuse is placed in the positive cable. Of course, you can have a negative cable, but in majority of the countries, the regulations state that the positive terminal must have a fuse. So no matter how big or small the power rating of the equipment is, batteries can potentially produce very high current that can cause a fire. If the consumer develops a fault in internal circuits, for example, if just consider that one of the consumers that is directly connected to the battery has a short circuit fault, then it's a disaster. It can even melt down the cables and all the terminals in the system, because you have a huge, massive amount of current with a considerable amount of voltage. This is a high power, and it can melt your cables down. So a DC circuit normally contains a main battery fuse, which is here, and after which it branches to the individual users. So here I've applied, just for example, a fuse for the inverter itself and a fuse for the charger itself. What is the advantage of this? Well, if there is a fault in the inverter, for example, this will be blown first, and this fuse will sort of survive. And then I know that, okay, my inverter needs to be reset, a fault happened here. But if you do not have individual fuses, you never know what happened, or you at least have to spend some time to troubleshoot and diagnose your system to find the fault that happened in your system. So it's always good to independently connect all the consumers with a sort of dedicated fuse to the batteries for troubleshooting purposes. Well, if you ask what type of fuses, they are normally the mega type fuses, you can also put a circuit breaker here with the matching current and voltage rate. It doesn't matter. It acts like a fuse. So, for the AC circuits, the circuit breakers are located near the entry point of the, let's say, external AC power. It could be a generator or it could be a power grid. So if you have, or if your system supports, for example, consider that you have U-Power High here. It's a hybrid device. Then it will accept the AC input from the power grid or, the shore power or any sort of external biaxial generator, for example. Then you'll need to have an AC circuit breaker to make sure that any alternations in current or voltage in your feeding side will not damage your equipment. And you also have to apply the same when you are supplying the consumers. You have normally a main AC circuit breaker, and then you might have also dedicated circuit breakers for each consumer. It depends on what you are powering and how much power you have. And if you want to calculate the amount of the current or rating of this fuse, that's simple. Take the surging capacity of this inverter and divide it by the output voltage, for example here, and it tells you that, okay, I'm going to accept some sort of 30 amps, and so I will apply something between 1.2 to 1.5 of this amount here. So something like 35 amps, 36 amps would suffice for this circuit. And It can be a single pole or double pole. Normally we use double pole for ACs. And well, we also discussed the current rating and the speed of blowing. It should be a fast blowing breaker here and in the interside as well. And again, for the PV area circuit breakers, so we have a sort of isolator. If you see here, this is the isolator, this is the oscillator, and this is also that sort of this can be isolator, this can be a circuit breaker or whatever. And it's also the same here, as I mentioned. So this is to disconnect your battery or your solar system for maintenance purposes or replacing an equipment or whatever. Otherwise, you are in big risk. If you short circuit during the maintenance process, these cables with the negative terminals, and if you do not have a smart battery protector, then it's not good. The parts will be damaged. So we normally use the isolators. So which one is preferred to the other one? These are specific for the mobile devices. We will describe them. So these keys are good for devices like vans and boats and etc. And these are for land-based systems, the circuit breakers. So if you have a land-based system, it's better you use a circuit breaker. Or if you do not have a land-based system, it's better you use these kind of isolators. So if I want to show an example, yes, it can be like this or this or this. So well, about and after oscillation, you also have a fuse or breaker here, and you need to calculate the amount of the current that flows from your solar panel to the battery or to the charge controller. Okay, you can simply do that by dividing the power of the solar array, no matter how you connect the solar panels to each other. If you have 4 pieces of 100 watts solar panels, no matter how you connect them in parallel series, you will get 400 watts. So it's easy to calculate how much power you have in solar arrays by adding up the power of each individual solar panel. And if you divide it by the system voltage, then you will get the maximum ampere or maximum current that is going to flow through the solar panels to your charge controller. Of course, you need to select a charge controller that accepts a higher current. So for this one, I would select a 100 amp charge controller. But for the fuse ratings and the cable ratings, we know that the cables coming from here and going to my system needs to tolerate 83 amps. And this is sort of calculated, and you are safe if you use a cable with 100 amps capacity. So a battery isolation switch can be used to isolate the battery, as I mentioned. So if you disconnect the battery main fuse, one would argue that, okay, the fuse would do the same. Yes, that's true. If you just replace or disconnect the battery main fuse, then this is open circuit. But this is more nice, and this is more safe, and this is more easier to operate than just opening the fuse. But it depends on your preferences, really. Normally we isolate the positive battery cable, as I mentioned, but this really depends on your local standards and regulations. And these also have a voltage and current rating. It's important that you check on the product labeling how much current and how much voltage this can tolerate, and should be in range of your requirements. Well, this is also an example of a rail-mounted or DIN-mounted circuit breaker for land-based systems, for battery PV systems. And normally, when the voltage is high, you use these sorts of fuse holders and breakers. And well, these are also the isolators for PV panels, for example. This also makes it easy. So we had a sort of, let's say, isolated here. You can use either these type of switches in your system just to make sure that you have safely disconnected the solar panel from your system. Okay, and then we have the surge protection devices. It's here. We will have another webinar that we will discuss this in more details, but in general, surge protection devices provide protection against the hazards caused by surges or, high transients and etc. And this is very common in the field. It frequently happens if your installation is outdoor installation, and depending on the elevation and the shape of the installation, you might experience some sort of transient. So if, for example, I want to mention some, if you have two clouds, for example, and you have your solar panel here, for instance, then a direct current flow from a cloud to your solar system can provide these high transients. Or if you have, for instance, a current flow between two clouds, this amount of current is massive. So you have some sort of wires in your system, and this is a conductor. And with this high current opposed to a conductor, you will face some sort of transient current or transient voltages in your system. And this always going to damage your system. So it's better, depending on the type of the installation, you have a sort of surge protection device which guides the high current to the ground. Normally, this let's say this device is open circuit, but when the voltage or current exceeds a certain amount, then that's short circuited and it guides let's say the current to the ground instead of to your system, and this protects your let's say your system. This is the application of surge protection device in your system, and there are lots of it in the market, and here you can see let's say a sort of surge protection device. And we also have this communication wirings. And what are they for? This charge controller here, and this inverter here, and if you have some other components in the system, they all have some parameters which matters for controlling the system. As an example, we have a battery temperature sensor connected to a charge controller, for instance. And it tells us that we should stop charging the battery if the temperature rises from a certain threshold. So it's important that this amount of value is communicated between the system, or this inverter can be shut off if the battery voltage goes below a certain threshold. So if you can see here, you have a communication cable that goes from the charge controller to this module, which is just a RS-485 module. I will describe it. And from the inverter to the module, and then you have a local monitoring system, and then you can connect it to any sort of application, a mobile device, or Bluetooth, Wi-Fi, etc. So these cables are not really carrying a lot amount of amperes or voltage or etc. They are just signal lines. And the protocol is Modbus. So Modbus is 2-wire or arguably 3-wire communication system. We have lots of slaves in our network and one master that is collecting the information from all of them. And the data is being transmitted by altering the voltage between these wires. So it's normally 5 volts or so. So these cables doesn't really bring any hassle to the system in terms of, let's say, the current capacity and so. But they provide the means to capture and monitor all the parameters of the system. What is the load voltage? What is the load current? What is the load power? What is the charging power of the solar panels? What is this voltage? How much energy I've got today from my solar panels? And all these parameters are going to be gathered together, and then you can access it using let's say software. Or if you have, for example, the Modbus tables, you can use even I don't know, software like Busbars to map the registers and read the registers that are containing the desired data, and then you can easily forward it to a SMTP server or FTP server, or you can use even the Epever's cloud monitoring system to collect all the data together online, using our IoT module. This is active, and we are using it for, let's say, the LED drivers. So, but regardless of that, these cables just carry a very little amount of current and energy, and they provide the means for monitoring the system and controlling it and configuring it, of course. So, we have not yet covered the ground, earth, and the safety of the off-grid systems, because this will also take some time to discuss it. We have different systems and different installations, and for each one it differs how the grounding would look like. And again, for the safety and these sorts of things, I think it deserves that we have another webinar for it. So it's already 1 hour and 70 minutes, and if I check here on my system, there are 97 people with us. That's pretty amazing. Thank you so much for your interest, and we are grateful to have you with us with this webinar, and please feel free to submit your questions, and we will try to provide answers to you as soon as possible. So with that, thank you so much for your attention, and I wish you a nice rest of the day.
Thank you.
Thank you.
Excuse me. May I ask one question?
Thank you very much. Yes, go ahead, please.
Actually,
Thank you.
Can you hear me?
Yes, I can hear you. Yeah.
Yes.
Thank
Actually,
you.
I asked the assistant of your presentation to share one photo because I have little details I need to show to you first before my question to understand exactly what I need to ask. But I don't know how can I share this photo inside the chat.
Well, we can do it inside it. Let's say, if you just please write your email address, my colleagues will approach you. Yeah, we can have a separate email, or we can communicate by email, or we can communicate by WeChat or WhatsApp. So
Okay, WeChat
yeah.
is better because I need to explain something to understand exactly what I need.
Okay, perfect, no problem. Just feel free to submit your email address in the chat section, and we will approach you.
Okay, I will.
Okay, no problem.